All right, good morning, everyone. So in this early morning, let's start with a quiz on the digital image processing fundamentals to wake everybody up, okay? This is some remaining contents of our last lecture topic, image processing, but we don't have time to do it in last class, so we put it at the beginning of this class. So you can join this quiz by scanning this code, this QR code. Will be some simple questions to assess whether you already get well understandings of the image processing fundamentals. So you can scan this QR code to join. All right, so has everybody joined yet? Great. If yes, then we'll start. Okay, so let's start our question 1. Okay, this is false. The axial channel alpha represents the transparency. Transparency is not the same with shade of the image. Shade basically means that you consider that there is some light source in the environment, then after this light source, like there is a sun, then there will be some shade of the object. That's the shade. But the transparency is another thing. That's how opaque each pixel is. So basically, they are different things. So the added channel represents the transparency, not the shade. So this is false statement. Okay, the frosty is our number 1, and midterm below me occurs again. All right, then let's check the question 2. Yeah, keep moving on, forget about the midterm, okay? The next goal is the final exam. Okay, this is true. So basically, the image processing is a kind of signal processing. When we treat all the images as some 2D signals, you may say that some images are 3D, right? The RGB and RGBA images. But even in some 3D image, when we process the images, we treat them as 2D signals. So that means the signals has like 2-dimensional in space. That's the width and height. And then for the channels, like the red, green, blue channels or alpha channels, we just treat them as some depths. So that it has like multiple depths. Each depth, it has some information. But overall, it's just some 2D signals. So, and actually all of the image processing methods we have learned, they are just some of the signal processing. So they can also be tried to extend to other dimensions to deal with some other signals. So the image processing just treats the images as 2D signals and then apply some certain signal processing methods. So this is true. Like the convolution we have learned, actually convolution is not specific for imaging. Convolution is basically a general type in the signal processing methods. Good, forget about the midterm. Okay, number one is HKUST. Then let's check our question 3. Okay, good. The majority can get it correct. This is false. Image processing is not only for machine interpretation. Big usage of image processing actually is for human interpretation. Right? So basically, that we edit the image, we process the images. One of the very important goal is that we let humans can see the images clearly and also can interpret the image information. So it's not only for machine interpretation. It's also for human interpretation. So that's why this is false. Okay, the HKUST is still our number one. And let's check the next question. Yeah, this may need some time, so the time limit is 1 minute. Okay, good. I think most of you can get the correct answer. Transformation matrix M for image scaling. So recall that we learned one big type of the image processing is called the affine transformation. Basically, the affine transformation is that you need to define what is this transformation matrix big M, and then this big M will be used to get the relationship between the new coordinate and the old coordinates. So let's recall what we have done in the image scaling. Image scaling means that for some original image, your scale is width and height, right? In this case, the new coordinate x prime, actually it should be some like scale factor a times the old coordinate x, and then the new coordinate y prime should be possibly another scale factor b times the original coordinate y. And we have to rewrite it using the matrix multiplication because we need to get this big M. So after rewrite it, that is we need to find like x prime, y prime. This vector should be M. Big M is a 2×3 matrix dot product with x, y, 1, right? So rewrite these two equations into some matrix multiplication, I believe it's easy to find that actually it should be like A0, 0, 0, B, 0. So that's why the answer is the first choice. The transformation matrix big M for image scaling should be that one. So actually it's also a type of the affine transformation, and we can easily find this transformation matrix. So the correct answer is this. Okay, the Mano Saba achieved the number 1. And let's check our final question. Okay, this statement is true. No padding means that for any input image, you will just ignore all the border pixels if they do not have the corresponding label. In that case, if you use some large kernel size, and that means actually there will be more border pixels that do not have the corresponding label. So basically just discard them, and then the output image size will be decreased. So you will get some smaller output image, right? So like recall that previously, if we use some 3x3 kernel, and if we do not apply any padding, then basically we will just reduce the size by 2 in both width and height, because we basically discard all the border pixels. And then just imagine if we use some 5x5 kernel size. In that case, actually, our output image will reduce the size by 4 in each dimension. That is both width and height, the size will be reduced by 4, because we will have more border pixels who do not have the corresponding label with the large kernel size. So this statement is true, just it further decrease the output image size. All right, let's check our final leaderboard for today's quiz. Okay, congratulations to Dave, today's number 1. Who is Dave here? Okay, congratulations. You have a very good knowledge about the image processing fundamentals. Great. Keep moving on. All right, so any further questions regarding this quiz? So any more confusion? Great, no more confusion, and I believe everybody wakes up after finishing this quiz. And then next, we can start our today's topic, move on to the convolutional neural network. So in this topic, we will continue to discuss how to implement an AI for image recognition and classification. So after all of the image processing methods, we go back to build the artificial neural network. This time, we use CNN, a full-name convolutional neural network, to train the AI agent to know how to recognize or how to classify the images. Now that the CNNs can also be used to train AI agent to solve some other problems, even though at the very beginning, CNN is designed for image classification. But actually later on, researchers find that it can also be used to solve other problems like the natural language processing, speech recognition, and even the recommendation systems, and so on and so forth. Actually, it can be solved many other problems in many other applications. And this is a typical CNN structure. In CNN structure, definitely it's some types of artificial neural network, right? So it's a sequence of the neural layers. For the inputs, if we use it for the image processing, for the image input, then the input is some 2D signal. We just treat it as some 2D signal. Of course, it might like contain some depth information. Like here, it actually has depth 3 channels here. After it accepts some inputs, this is a 2D convolutional neural network because it can accept some 2D image. It will have some like convolutional layer and then some pooling layer. As you can see, it's a sequence of convolutional layer and pooling layer, so on and so forth. Possibly many convolutional and pooling layers concatenated together. All of these convolutional layer and pooling layer, as you can recognize here, actually they are 2D. So it's very different with the multi-layer perceptual neural network. In multi-layer perceptual neural network, each layer is 1D, right? We know that it's 1D, has like some nodes, but here each layer actually accepts some 2D. So again, you can treat it as one node, but this node is somehow not a neuron. A neuron is just 1D, but somehow it's some 2D. And guess what is each node here? Each node is just a kernel. Exactly the kernel we have learned in image convolution. But still, after a sequence of convolution layer and pooling layer, we still need to flatten. At the end, we still need to flatten them to 1D and then connect with some fully connected layer. Because we know the fully connected layer, that's the dense layer, has to be in 1D. And then this is a typical layer with the neurons. And then after like some 1D layers, at the end, we will have the output layer. So again, it follows that we have some input layer, we have an input layer, we have an output layer, and all the middle layers, they are just called hidden layers. But for the hidden layers, we have more types now. And later on, I will introduce one by one what is this new hidden layers. There's a convolutional layer and pooling layer. So the convolutional neural network, they were developed actually already in last century. That's far away from now. So in late 1980s, but somehow they were forgotten about due to the lack of processing power. So that means even though at that time, at last century, researchers, they developed CNN, but they don't have any computation power to run such a big model. So they just put it there, forget about such model. But later on, with the development of GPUs, like after we have the powerful GPUs, then the research on CNNs and deep learning was given some new life because now we have the computation power to run such complex, such big models. So CNNs are used in many applications, like the object recognition in images and videos. Natural language processing actually can also use the CNN, like the speech recognition in Google Assistant or Amazon's Alexa. Actually, CNN can also be used to play games, like the defeat of the World Go champion by DeepMind at Google. Actually, they also leverage CNN techniques. And they also be used in the medical innovation, like from the drug discovery to prediction of the disease. So CNN is already like in wide applications nowadays. And what are CNN? Like when we're talking about CNN, what exactly is this type of artificial neural network? So it's very much related to the standard artificial neural network that we have previously encountered in the multi-layer perception. But for CNN, when we're talking about CNN, we mean that it must have at least one of the layers with convolution operation. So as long as we put some convolution operation in the neural network, then it's already called the convolutional neural network. So that means at least one of the layers must be convolutional layer. Then it's CNN. And convolutional operation is exactly what we have learned in last class, image convolution. So hope you still remember. Like here, if we have an interested pixel here, like this is an interested pixel, then we do the image convolution by referring to the kernel. Like this is a convolutional kernel 3 by 3. The kernel is 3 by 3, so that means we must find 3 by 3 neighborhood of the interested pixel here. For example, we find that, okay, this is the 3 by 3 image patch, the neighborhood of this point, and then we slide over the kernel until it overlaps with such image patch, and then we do the element-wise multiplication and summation, like what we have done here. Then the output pixel should be 1 by 1 multiplication, like 180 times -1, so here. And we just do this multiplications, add them together to get the output value. So this is the image convolution, right? And then for convolutional neural network is that as long as we have at least one convolutional operation in the neural network, then it's already called CNN. Now, how does the convolution fit into CNN? Like, how can we have some convolutional operation in a neural network? So first, we should recognize that each pixel in an image is a feature. So we know that whenever we are talking about the machine learning algorithm, we need to find what is the feature of the input, or the feature you extracted from the input, right? Previously, when we're dealing with some like very traditional machine learning models, the feature is very well defined. You have a data set. You have many columns, like the height, the width. These columns are features, right? For a data point, like the height is some feature, or the weight is some feature. These are some well-defined features. But what are features in images? Features in images is just every pixel. Every pixel in an image has some values, and this pixel is already a feature for this image. And that means for any input data, every pixel is an input node. So as you can see, the input layer is arranged in 2D space because the image itself is 2D, right? It's always like has 2D, and then every pixel is just a feature, is a node. So these nodes are arranged in some 2D. The result from each convolution is placed into the next layer in a hidden node. So now each feature, or actually feature is just pixel. Each feature or pixel of the convolved image is a node in the hidden layer. So that is, after you perform image convolution, of course, you still get some 2D data, right? The image after convolution is still some image, convolved image, and still each pixel is just a node. So all the nodes are arranged in some 2D space. When we're talking about 2D space, that means we regard the channel like RGB, the channel as some depth information instead of the spatial dimension. The spatial dimension, we always just consider it as 2D. Then what are the numbers in the kernel? We know a kernel has different entries with different values. Like a 3 by 3 kernel has 9 values. What are these numbers? They are the weights. They are the weights connecting the feature of the input image and the node of the hidden layer. And these weights that connect to the nodes need to be learned exactly in a regular neural network. Like previously in MLP, we know that all the layers, they are just 1D, right? And all the edges connect some node in previous layer with some node in the current layer. The edge has a weight parameter. The weight parameter assigns the weights to some input, decides how important each input or each feature is. And the weights should be learned during the training. And now in CNN, the weights are just the numbers in the kernel. And still, the weights, you can regard them as some edges connecting the nodes between layers. But since now all the nodes themselves are already arranged in 2D, so these weights are also in 2D. These weights are exactly the kernel. Kernel, we know that's always 2D, some matrix. And why we also call it weights? Because actually these weights are also assigning the weights or decides how important each feature is. If if we look at this figure, we try to get a sense. Like when you try to get the output value, you are doing such multiplication, right? And then add them together, do the sum. This is actually what we have done in the weighted sum of the multi-layer perception neural network. If that's now this node is a pixel. Each pixel is just a node. This node is associated with a weight with -1, and this node is associated with a weight with the value 0, so on and so forth. So each of these nodes, like we have 9 nodes here in such 3x3 image patch, each of the nodes actually are connected with a weight. And this weight decides how important these features are. And since each entry in a kernel, like we have 9 entries here, then that means we have 9 weight parameters in this kernel. Each entry is just a weight parameter. And the weight parameter should be learned, should be updated during the training process. Like when we're training a neural network, we do forward propagation, and then we do backward propagation. During backward propagation, we update all the parameters. So that means we will update all the weights, all the kernel values during the back propagation and in training a CNN. So yeah, this is very important. You need to get understand before you know how to train a CNN. So when we're talking about training a CNN, we already include that we should learn the parameters of all the kernels, the entries in the kernel. So the kernel values are automatically learned by CNN. So until now, any questions so far? Great. If no question, let's move on. Like this is an illustration of a convolutional neural network. Suppose we have an input image has a size 4 by 4 by 3. Note that the last dimension is a depth. Depth means that it has 3 channels. But still, we treat the image as some 2D signals. So still, it has like width and height, the spatial dimension as 2D, but it has like 3 channels. And then for the first convolutional layer 1, suppose we set 2 kernel maps here. And each kernel map with the size 3 by 3 with the depth 3. So the kernel size 3 by 3, and we have to set the depth 3. Because in convolutional layer, the kernel depth must be the same with your input depth. So like this input layer, you already have like the depth 3 for all the input image. Then in this convolutional layer, you must set the kernel depth also as 3 so that you can map them one by one. But the number of kernels, you can just decide by yourself. Like here we decide, okay, we should use 2 kernels here. And then the 2 kernel maps, kernel map 1 and kernel map 2 will be arranged. They will work as the weight parameters. Then in this kernel map 1, it has like 3 channels, right? It must correspond with the input channel. And then they will do 1 by 1 mapping. So that means the first channel, the red channel, will be convolved, the image convolution convolved with the first channel in the kernel. And then the second channel, the blue channel of the input image, will do the convolution with the second channel here. And then the third one will do the convolution with the third channel here. So 1 by 1, like the kernel depth must be the same with the input depth. After that, you will have some convolution output. So this is what you get the output for this layer. And we already assumed that we're doing some zero padding. So to make sure that the output has the same size with the input. So that means, okay, actually still it maintains 4 by 4 size for the output image. And for the kernel map 2, we do the same thing. Like the red convolve with the first channel, the blue convolve with the second channel, so on and so forth. So after the kernel map 2, we will have this, again, some outputs, like 3 channel output. But note that the true output of this convolution layer is not the split channels. For each kernel map, after convolution, we will do the sum, the pixel-wise sum. So that means we will add the 3 channels together to get one image, one output image. Actually, it's just some features we extracted and we store in this image. And then again, for these 3 outputs, actually they're just some split channels, right? We will do pixel-wise to add the values up to get another 4x4 image. So that means the true output of the first convolution layer with the shape 4x4 by 2. 4x4, the image size is still 4x4 because we have done 0 padding, but the depth or the number of channels becomes 2. Then I guess you already know what should be the depth after each convolution layer. The depth after each convolution layer is the number of kernel maps you have applied in this layer. Like in this layer, we apply 2 kernel maps. Then that means the output of this convolution layer should have the depth 2. Each kernel will produce 1 channel output. So this is the rule of getting the output shape in convolution layer. Then we have a second convolution layer. Suppose now we apply 3 kernel maps. 3 kernels, each still with the size 3 by 3. The depth of the kernel should be 2. The depth of the kernel should always be the same of the depth with the input for the current layer. The input for such convolution layer 2 has a depth 2, right? Just here. Now, this layer is the input for the next layer. They have the depth 2. So all the kernels here you apply should have the depth 2. And then you apply 3 kernels. So that means you will get 3 channel outputs. Again, like for this kernel map 1, you do this 1 by 1 image convolution for the 2 channels. And then for the kernel map 2, you do 1 by 1 convolution to get some 2 depths. And kernel map 3, you get some depth 2. And you do some pixel-wise sum. And after that, you will have the output here. The output should have the shape 4 by 4 by 3. 4 by 4 is again the image size because we have done 0 padding for the layer. So that means we keep the image size the same. The image size is still 4 by 4. We won't decrease any of the spatial size, but the depth becomes 3 because we have applied 3 kernel maps. The depth of the output should always be the same with the number of kernels you have applied. So this will be some basic rules of like how to decide the depth of kernel in each layer and also how to get the depth of output in each convolution layer. But still we have like many details unknown, right? We only know some rules about the depth, but we don't know what exactly have been done here, what exactly are the convolution layer. So let's move on to learn more details. The intuitive idea of convolution layer will be like this. So a deep neural network, we have input layer, we have output layer, we have many hidden layers. We can regard that each hidden layer is trying to extract some features from the input. Like intuitively you can think about that possibly the first hidden layer tries to extract some edges information, while the second hidden layer tries to get the combinations of the edges, and then the third hidden layer tries to get the object models. And after we extract the useful and enough information and features, then we can connect it with the output layer to do the classification. So this is the intuitive idea of the deep neural network, especially that for convolutional neural network, actually we can visualize what is the hidden output for each layer. Because each of the convolutional layer, actually the output, we can also regard as some images, right? Like it should be some like 4x4 image. Actually, we can try to visualize them, try to get a sense like what features have been extracted by the convolution layers. Convolutional neural network, like the typical structure will like this. The input layer, some 2D image, with the depth. Like here, we have the input image with the size 28 by 28, depth is 3. After the input layer, we connect with some convolution layers and pooling layers. And after the sequence of convolution layer and pooling layers, we will do the flattening, flatten everything to 1D, because the fully connected layer can only accept the 1D. So after that, we can get the fully connected layer, and then after maybe a few fully connected layers, we will get some output layer. Output layer will do the final prediction. That's the classification results. So there are 3 main types of layers to build the convolutional neural network. As you can see from this figure, after input layer, we will have convolution layer, and then pooling layer, and then fully connected layer. At the last, we have output layer. So basically, we need to learn the 3 types of layers in order to build the CNN. Actually, the fully connected layers, we have already learned it in MLP. So for this course, we need to learn what is convolution layer and pooling layer. So let's see the convolution layer, the input layer first. Basically, the input layer is quite simple. It's just the input image. Like you place the input image into this layer. It can be some single layer 2D image, that means grayscale, or some 3-channel 2D image, that's RGB color. It can also be 3D. What cases will it be 3D? If it's 3D, then that means the input is a video. So except from the image information, you also have another dimension representing the frame or the time. So when it's the 3D, that means it's video. Now that's in the example on the last page, like the example here. The input images are 3-channel 2D images. Like the size is 28 pixel by 28 pixel, and it's some RGB color because the channel is 3, we have seen. And then the kernels in convolution layers need to be learned. The kernels, they must be in the same depth as the input. And in the example here, the first convolution layer we have used, actually we apply 10 kernels here, and each with the size 5 by 5 with depth 3. The depth 3 must be the same with your input depth. So this is the kernels in convolution layer. Then let's have a deeper look at the convolution layer. So the convolution layer, what exactly are they doing? Like after accepts the input with the size and depth like this, then we applied some kernels with size 5 by 5 with depth 3. The kernels in convolution layer, they always extend the full depth of the input column. Why? Because we will apply multiple kernels here, and the number of kernels will just be the depth of the output. So here, after each kernel, basically it's just do the image convolution, right? Image convolution, this image convert with this kernel, and we know that the image convolution is that for any one number in the output, the results should be adding the product between the kernel and a small 5 by 5 by 3 chunk of the image. So that means actually for any single number here, we are doing 75 multiplications, and then we add these 75 multiplications together to get just one number. And then why we see that kernels always extend the full depth of the input volume? Because this is only for one kernel. For one kernel, you done such convolution, and you will apply multiple kernels. Like in the image here, we applied 10 kernels. So that means at the end, you will have the depth 10 of the output, like this. So the final output of this convolution layer will be some 24 by 24 by 10 image volume. Each resulting image is called the activation map. Like you just concatenate them layer by layer after convolve over all the spatial locations. The first kernel, you will get some results here. The second kernel, you get some results here. And in total, you apply 10 kernels. That's why the output has depth 10 channels add together. And note that the output size is 24 by 24 because for this example, we assume that we have done no padding. So if no padding is applied, then the output image size will be reduced. And since we have applied the kernel 5 by 5, that means we will decrease the output size by 4 in each dimension. So that's why from 28 to 24. So for this convolution layer, the input image is some 28 by 28 by 3. The depth is 3, and we apply 10 kernels. That means we apply 10 with size 5 by 5 with depth 3 kernel. And with assumption that we don't do any padding, we ignore those pixels that do not have the 24 neighboring pixels. And the output will be 24 by 24. This is the spatial dimension. The image size is 24 by 24. And the depth will be the number of kernels we applied, that is 10. And for each of the values we get in the output, it's just by image convolution, of which we learned in last class, the convolution. All right, so this is for the convolutional layer. So any questions so far regarding convolutional layer? Great. If no question, then maybe let's take 5 minutes break so that you have some time to absorb the convolution layer. After 5 minutes break, we will continue with some new concepts that we will do in the convolution layer.
是不是因为就要这个3个权重可能不互相相信？对，对于不一样的颜色，可能分配不一样的kernel。对，因为这些kernel的其实都是会被学出来的。那比如这个，那我们怎么把它这个一个image产生的这个 depth 关？就是它和它对应的convolution就变成了它，它和它对应的convolution变成了它。那我们就这两个是有不一样的初始值。对对对，他们都会有不一样的初始值。就是每一个 entry 它都会有一个不同的 random initialization。但比如说这个之前是讲那个就是MLP 的，就是它是比多个linear的东西，那最后得一个linear，那么这些东西它也是linear，它那考虑是不是其实还是算一个 linear， 但是对对对，说得好，所以其实每一个 convolution node 它其实也是会有一定的。就是你不能 assume 它全是linear。对对对，其实那就是如果全是linear，如果是的话，这个是不是相当于就是一个？对，这个其实就相当于是一个大 convolution 就可以代表。对，但其实每一个 kernel 它会有一个。那这个东西有bias 其实也是有的，对，就相当于每个 kernel 你是还是会选。
多的 bias，这样
是有9个群，就以这个为例，有9个群。
对 bias 就一个，其实是这个 bias 对这3个都不可能，就是它每一个 kernel map 有一个 bias。
它那个 PPT 那个图片上不是，它第一步先把这个 feature 弄出来，然后再把这个 feature 组合，它是怎么组合出来的？那你说这个东西应该是一个信息是不断减少的一个过程，它应该没法再拼回去。
这个它的信息不是这个，它的信息是越来越全面。就是一开始的时候，可能我们只能 extract 一些非常零零散散的 edge，这些 edge 对我们来说没有任何的意义。但是之后它就试图把这些 edge 拼凑在一起，拼凑成一个完整的东西。就是它每一层都在使得这个 feature，它的 feature 数量在越来越少，但是它其实是因为它在抓取越来越全面的 feature，可以。
关于这个 feature 信息的越来越多，
对。
关注的东西越来越少。对，就是所关注的东西获得剂量多的。
对，就是这个 feature 它在越来越有用，虽然它数量在减少。
哦，不对，对于同一个来说还真是不一样。对于同一个 pixel 的真的是零点。确实应该是一个。
比如你4、5、4、5，跟你2、3、3，把4个kernel放在中间，你就把那个4、5、4的一个整个的那个。
All right, let's continue. So we have already learned some basic mechanism in the convolutional layer, but there are some more possible operations we will add in the convolutional layer. The first one is called the stride. Stride is the amount of movement between applications of the kernel to the input image. What does it mean? So let's imagine what we have done in the image convolution. Image convolution is that you imagine that you are sliding over the kernel over the whole image, right? Move it step by step. And the stride is that actually it's not necessary that each time you just move it by 1 pixel. You can jump over some pixels and then do the image convolution. So this is exactly the stride, which is similar with previous what we have learned in the NumPy stride. NumPy stride is also that you are selecting the elements, possibly like every 2 elements or every 3 elements. So this stride is that you are doing the kernel overlapping with the image every 2 pixels or every 3 pixels, so on and so forth. You can set the stride. The default stride in 2D is just 1, 1 for the height and width movement. So that means by default, we just sliding over the kernel 1 step by 1 step, so that each iterative pixel will get 1 chance of overlapping with the kernel center. But we can adjust this stride. The kernel is moved across the image left to right, top to down, with a 1 pixel column change on the horizontal movements and 1 pixel row change on the vertical movements by default. But if we want to change the stride, then it will have an effect both on how the kernel is applied to the image and in turn the size of the resulting output. Because if you jump over some pixels, then actually the output image will have some smaller size. And the stride can be specified in characters on the comp2d layer, where the stride argument and also it can be specified as a tuple with height and width. So actually you can set different stride values in the 2 dimensions. Then you may ask that why should we set the stride to some larger number? Why not just let it be default 1 by 1? The reason is that the larger strides lead to some lesser overlaps, which mean some lower output volume, because you can reduce your output size. Then it causes less memory. There are less memory needed for the outputs. In that case, actually it can try to avoid overfitting. We know each pixel is already a feature, right? Each feature is associated with like many parameters. If we try to reduce the output volume, that means actually for each layer, possibly we will reduce the number of features. And then we can in turn reduce the number of parameters. So actually it's a way to avoid overfitting, especially in case of the image processing having some large number of attributes. So that means if your input image is already very large, it's okay, you can set the stride to some larger number to avoid the overfitting. That means you don't need to focus on every minor details of the feature. Let's see the effects of the stride. So it may not see very clearly because I use very light blue color to represent the stride. Actually, it has some difference. Like this 3x3 image patch with the light blue, all others are white, but it's not very clear, you see. I guess it will be more seeable in your own computer. We can try to like draw it here. So now suppose an input image is inside 7x7 and the convolution is performed using a 3x3 kernel. By default, we know that the stride is 1. So that means at the beginning, the kernel is here. Sorry. Okay, we can just draw it. The kernel is here, overlap with the first 3x3 image patch. If you use a different color, will be better. Okay. And then the next step, it just move 1 pixel away. So next it will go to, oh sorry, it's still black color, but anyway, just. So next it will be here. The kernel slide over, overlap with this 3x3, and then the next step comes here. Okay, this overlap with this 3x3 image patch, and then the last step comes here, and then finally in the row dimension it goes to here. So after that it finishes sliding over for one this wise, and then next step of course it will start to like overlap with this one 3x3. So each time it just moves 1 pixel wise, and that is why the output is 5x5 if we do not apply any padding, right? Because we can only just slide over the kernel for these 5 steps. And then let's see what will happen if we use a larger stride. Suppose now we set the stride to be 2 in both dimensions. In that case, the first step is overlap with the 3x3 patch here. After that, it will stride 2 pixels. So that means the next step, the kernel moves here, overlap with this 3x3 image patch. And then it further moves 2 pixels at the next step and moves to here. After that, we are done. When the stride is 2, we move the kernel to 2 pixels at a time until we reach the boundary. And in this case, the output will be 3x3 because we can only slide over it for 3 steps in each dimension. So as you can see, if you set the stride to a larger number, actually your output will get smaller. And what will happen if we set the stride to be 3? Then the first step is overlap with such image patch, and then it moves 3 pixels, so it comes here. And then we cannot continue the next step because if we further like move it 3 pixels away, then it will somehow go this one, the kernel's first column overlap with this column, but somehow it's out of boundary, right? But until this step, actually, we haven't reached the boundary. So that means, actually, this does not fit with the input image. If we use stride 3, then it just simply not fit. So we cannot apply 3x3 kernel with stride 3. It does not fit. It does not reach the input image boundary. And if you fold the slide over, it will exceed the boundary. So it's not fit. And there is a useful formula for determining the size of the output image. Like we already know, if we use different stride, we will get different output image size, and we can depend on this formula to get that. The output size will be the size of input image's dimension minus the size of the kernel dimension divided by stride, then plus 1. And for example, the size of image dimension is 7, which is the example here, and the size of kernel dimension is 3. Then the output size can be calculated here. So if we use stride 1, the output size is just 5 by applying this formula. If stride is 2, output size is 3. If the stride is 3, the output size, we get the value 2.33, which is a decimal, not an integer. That means it does not fit. We cannot give the stride 3. So this is, we can add such operation stride when we're doing the convolutional layer. So any questions so far regarding the stride? Great. Then until now, we just assumed we don't apply any padding. But sometimes we want to keep the border pixels information. We don't want to simply discard them. In this case, we need to apply padding. And in HKUST, sometimes for simplicity, we just directly apply 0 padding. But actually, there are some other paddings, right? We have learned like the replicating padding, reflecting padding, also the mirroring padding. But here we just use the 0 padding as an example to give you, like, to illustrate that what should be the output image size if we apply padding. So when a kernel converts a given input image, the dimensions of the output images are reduced if we do not apply padding, because we just ignore some pixels without the labels. Now, how to preserve the size of the output image? We do padding, and here we consider 0 padding. The 0 padding occurs when we add a border of pixels all with value 0 around the boundaries of the input image. And if we are using HKUST to implement CNN, actually there is an argument called padding. If you use that Conv2D layer, and there are 2 values for that argument. The first is called valid. If you let the padding argument be valid, then that means no padding at all. Just don't apply padding. Another possible value for the padding is same. Same means that pad the original input with zeros before we convert, so that the output size is the same size as the input size. So know that we can simply let it be same. That means you don't need to calculate how many pixels you should pad, because the HKUST will automatically calculate this value. If you let it be same, then it will just automatically calculate, okay, what should be the number of pixels to pad if the output size should be the same with the input size, because it depends on the kernel size, right? So this would be like, you can specify the argument padding to be these 2 possible values, depending on whether you want to apply padding or not padding. So suppose we do padding with some 1 pixel wide border and with the stride 1 when we're doing the convolution, then what is the output image size? The size of image dimension we know is 7. The size of the kernel dimension is 3. And we pad with 1 pixel border, just like we show here. Then the output image size, according to the previous formula, we're still applying this formula here. It should be 7 plus 2 minus 3 divided by 1, then plus 1. Note that the input dimension becomes 7 plus 2 after we apply padding. Even though we said that it's padded with 1 pixel border, but it's on both sides, right? If you pad on the left side, then you will also pad on the right side. Like if you pad in up, then you will also pad at the bottom. That's why actually it should be 7 plus 2. This would be the new image dimension, and then minus kernel dimension. So after that, the output image size will be 3. So now the output image size keeps the same with the input image size after padding. And in general, it is common to see that convolution layer with some stride 1 kernel of size some k by k. Actually, you already find that actually this k is an odd number, right? When we're applying the image convolution, actually we never use some even number of the kernel size. Yes, that's a convention. So when we're designing some kernels, it's always some odd number, like 3 by 3, 5 by 5, 7 by 7. Just use some odd number here. And then we usually do some zero padding with k minus 1 over 2. In this case, it will preserve the size spatially. That means your output image size will be the same with your input image size. If we set, like, for example, the padded border size, if k is 3, then we should zero pad with this 3 minus 1 over 2, which is 1 pixel border. Then we can keep the output image size spatially. And then if k is 5, we should pad with 2 pixel border. If k is 7, we should zero pad with some 3 pixel border to keep the output size spatially. So let's look at some all-in-one example. If our input image size is 32 by 32 with 3 channels, and we apply 10 kernels, each of the size 5 by 5 with a depth 3, suppose the stride is 1, and suppose we pad with 2 pixel border. Then according to the formula, the output size should be 32 plus 2 times your padding pixel. That's 32 plus 4 minus kernel size 5 divided by stride 1 plus 1, which is 32. And then the depth of your output is the number of kernels you have applied. So here you apply 10 kernels, so the depth will be 10 here. Then the output volume size will be 32 by 32 by 10. Then what is the number of parameters in this layer? The number of parameters is how many values are in the kernels, right? Each entry in the kernel is just one weight parameter. So basically you need to count how many entries are in the kernels. So each kernel with the size 5 by 5 with the depth 3, so that means each kernel has like 5 by 5, 5 times 5 times 3 weight parameters. And don't forget the bias. Actually, this concept of bias also applies to kernels. Like previously, when we were learning artificial neuron, we know that each artificial neuron is always associated with a bias parameter itself. The same for kernels. In convolution layer, each kernel will also be associated with one bias parameter. So that means after the image convolution, actually, we will add the bias value to each entry of the output. So that means each kernel should also consider this bias parameter. Now each kernel has 76 parameters, and we have 10 kernels, so there are in total 76 times 10, which is 760 parameters in this convolutional layer. So this is how we can get the number of parameters in convolutional layer. So any question regarding this all-in-one example? Great. If no question, then actually just some students asked during the break, which is a very good question. So we know image convolution basically, again, is some weighted sum, right? You do some weighted sum between the input image and the kernel. That's some linear operation. And we said that in a neural network, if all the operations are linear, then basically it's equivalent with one big linear transformation. The combination of linear transformation is, again, linear transformation. It's some linear operation, but definitely we need nonlinearity. Otherwise, 2 convolutional layers would be no more powerful than 1 convolutional layer. Then how to add the nonlinearity? We already learned that. Activation function, right? The nonlinearity is not its own distinct layer of CNN, but actually the nonlinearity comes as a part of the convolutional layer as it is done in the artificial neurons, just like a normal artificial neural network. So we need to use activation functions to add a nonlinearity. So we have learned sigmoid, ReLU, and also the tangent H. So now that in CNN, usually we will use ReLU for the convolutional layer as the activation function because the ReLU is very efficient. It does not require any expensive computation, and we also talk about that actually ReLU can alleviate the vanishing gradient problem compared with sigmoid and tangent H. So here is another advantage is that ReLU can speed up the convergence of the stochastic gradient descent algorithm. So this is some empirical results, the convergence rates. So the horizontal axis represents the epochs, and then the vertical axis represents the training error rate. So if we use sigmoid, then the error rate will decrease with epochs like this, but ReLU decreases much faster. So ReLU, due to its simplicity and efficiency, it can speed up the convergence by a large margin. So in CNN convolutional layer, typically we will use ReLU as an activation function to add the nonlinearity. Alright, so that's about the convolutional layer. So convolutional layer, let's summarize it a little bit. Convolutional layer is that we need to apply some number of kernel maps, the kernels. The kernel has some size. We need to decide the size, like 3 by 3 or 5 by 5, or maybe other size. We need to decide that. And then the depth of the kernel must be the same with the depth of your input for this layer. After this kernel's convolution, right? The kernels basically they're doing the image convolution with the input image. After that, the kernel itself has a bias parameter. So that means after image convolution, all the outputs should also be added with the bias term, the value, and then it will be passed to an activation function to add a nonlinearity. And that will be the true output of a convolutional layer. And in the image convolution, like during you're doing that, there is also a concept called stride. So that means when you're sliding over the kernel, it's not necessary that every 1 pixel you do the convolution. It can be like every other pixel or every like 3 or even 4 pixels you do the convolution, so that the output size will be decided by your input image size, your kernel size, your padding size, and the stride number. So this is how we can decide the output image size. Alright, so any questions so far regarding the convolution layer? Great. Convolution layer is definitely the most important part in a convolutional neural network. It defines what is a convolutional neural network, and usually it's the most complicated part. Then the remaining, we still have one new type of layer that is called pooling layer. Usually after convolutional layer, we will concatenate it with a pooling layer. What is useful? The pooling layer is a key to ensuring that the subsequent layers of the CNN can pick up some large-scale detail than just edges and curves. Because each convolution layer it tries to extract some features, right? The features usually contain some edge and curve information of the input image, but it's not necessarily so useful for doing the classification. Usually, if we want the neural network to do some accurate prediction, it requires some large-scale detail. That is how you can combine all these very minor details into some useful features. Usually, these large-scale features will be done by pooling layer. So it does this by merging the pixel regions in the convolved image together, considering that it's like shrinking the image before we attempt to learn the kernels on it. And there are two popular pooling layers. Both of them are very simple operations. The first is max pooling. Max pooling is done by applying a max filter to non-overlapping subregions of the initial representation. Like if we have an 8x8 image like this, and then if we set the pooling size as 2x2, then that means it will separate the input image into these non-overlapping 2x2 subregions. Like here, it can divide it into these 4 regions. And then the max pooling, that it apply max filter, get the maximum number of each subregion. Like the first subregion, this 2x2 subregion, the max number is 20. So 20 will be put here. And then the next subregion maximum value is 30, so 30 put here. So this is the max pooling. We select the maximum number in the subregion. And another type of pooling layer is called average pooling. Average pooling is done by applying the average filter to non-overlapping subregions. Like average pooling is that for the first subregion, we get the average of these 4 numbers, like 13 put here, and so on and so forth. So as you can see, after pooling layer, the output size is reduced, right? If we apply a 2x2 pooling size, then the output size will be reduced by half. Actually, that's the purpose of the pooling layer, because previously we believed that we don't need so minor details of the features. We don't want all the like edges, the curves, some like very minor, unuseful information. We want some large-scale details, and we do this by pooling layer to shrink the image to get somehow a smaller output size. But we believe that all the features now are more useful to do the prediction. So the pooling can also tolerate some local distortion and translation of patterns of interest. Because after you combine them together, after you combine the information in a subregion together, basically it can like be more allowable for the local distortion. And it can also reduce the computational load, memory usage, and the number of parameters, because after you apply pooling, definitely the output size will be smaller, so the memory is less, and also the computational load will be less, the number of parameters will be less. So it can also be used to save the memory and computation power. And another reminder is that pooling layer only reduce the size, it won't change the depth. The depth will keep the same after the pooling layer, because basically what we have seen here is that it only tries to operate on the subregion in the spatial dimension. It does not operate on the depth. So the depth will keep the same after pooling layer. This is a pooling layer. If we have a 224 by 224 input image for this pooling layer, and the depth is 46. Then if we apply a 2x2 pooling size, the output image should have the size 112 by 112. The depth won't change. The depth still keeps as 64. So any questions so far regarding the pooling layer? Great. Then the last type of layer, we already learned it, so this is quite relaxing. Fully connected layer or a dense layer, actually we have used it a lot in the multi-layer perception, right? So it's a traditional multi-layer perception that uses the softmax activation function in the output layer if we want to do the multi-classification. And fully connected implies that every neuron in the previous layer is connected to every neuron on the next layer. And the output from the convolution and pooling layer represents some high-level features of the input image. We can imagine that all the convolution layer and pooling layer, they are just trying to extract the features to get some useful information. And then the purpose of the fully connected layer is to use these features for classifying the input imagery into various classes based on the training data set. In summary, convolutional together with pooling layers, they act as feature extractors from the input imagery. Each layer extracts some information, and the information will be smaller and smaller, but in the meantime, more and more useful. While the fully connected layer will act as the classifier to give us the final prediction results. And then the overall training process of CNN is just like what we have done in the multi-layer perceptron. First, initialization. We need to initialize all the kernels and other parameters like weights, like biases, with some small random values, do random initialization, and then start training. The network takes a training imagery as inputs, right? We always input the data one by one, then go through the forward propagation step. Forward propagation step means that it needs to finish this calculation, convolution, image convolution, and then ReLU activation function, and then pooling operations along with the forward propagation in some fully connected layers. After that, after this forward propagation, it will find out the output probabilities for each class. That's the final output at the output layer. After forward propagation, then it calculates the error, total error as the output layer. Note that, of course, we have to define the error function or the loss function at the output layer. After that, it will update all the parameters by backpropagation. So use backpropagation to update all kernels and weights and other parameters in order to minimize the output error. We know training a neural network, the ultimate goal, or we can say the only goal of the neural network is to minimize the error function. And the same for CNN. And then we finish one step. One step is forward propagation and backward propagation for one data sample. We need to repeat the steps with all images in the training set. After we pass the whole training data set, we finish one epoch. And possibly we will do lots of epochs until we get convergence or until we get some expected results, the accuracy or a small error. So this would be the overall training process of CNN. All right, so this class we can just end here. So basically, I believe you all get the, theoretically speaking, you all get how the CNN runs, what is the CNN. But next class, we will do some like practical things in the handwritten digit recognition using the CNN. Next week's labs, Monday and Tuesday will be the Lab 8, so we will release Lab 8 by today and also send you a reminder. Lab 8 will also be a graded labs, so later on I will send you the reminder. So please remember to attend Lab 8 in next week, and see you in next week.